Čekaj, kam ćem dati? Na drugu stranu. Ne, samo prvi. A tu greš tem naprej? Okay, so we can start? Yeah?
Yes.
Okay, so this is part of our research program. It's very interdisciplinary, so interdisciplinary that will actually take two of us to do this presentation. So I don't know really much about parallel programming on the GPU, and I hope that Rok doesn't really know much about Bayesian statistics, although we are both learning. So this is part of our ongoing research program and a small part of our ongoing applied project entitled Parallel Draws from the Polygamma Distribution for Faster Bayesian Multinomial and Count Model Inference. So I imagine that not all of you are familiar with all of these terms, so I'm just going to do a brief introduction, maybe starting with Bayesian statistics. Maybe a show of hands, who has worked in Bayesian statistics or used the Bayesian model, heard about Bayesian statistics? Okay, so I'm going to start with two bold claims. Machine learning is becoming increasingly statistical. If you go to top conferences and read top journals, a lot of machine learning applications are now completely statistical. And statistics, applied statistics, is becoming increasingly Bayesian. Okay, so from that I will conclude that Bayesian statistics are becoming even more important. Why bold claims? Because I didn't take the time to provide any evidence to support this, but I'm pretty sure that these two are correct. Okay, so why are Bayesian statistics that important and useful? So one thing is that they're conceptually very simple. So every Bayesian model starts with kind of what we feel how the world works, a parameterized view of the world, or even a non-parametric view, and then some prior opinion about the parameters, and from that, using simple probability, so just the Bayes theorem, we can derive the posterior probability, which is basically what we have learned from the data. Okay, so I've been teaching Bayesian statistics for 2 years now, and I see that this conceptual simplicity is very useful when teaching statistics to machine learning experts or even computer science students. So it's much simpler than frequentist statistics. They can cover much more ground and have a more fundamental understanding of how the models work using this Bayesian approach. The other thing is that the results from these models are relatively easy to interpret, and the decision theory, because you have the full posterior distribution, is very simple. So if no matter what distribution you're interested in, whatever property of that distribution you're interested in, if it's higher than 50%, if it's between 10, whatever thing you're interested in, you can just compute that from the posterior distribution. Okay, it also has some disadvantages. The major disadvantage is that Bayesian models tend to be intractable in practice, even the simple ones. So we have to use either approximation or computation-intensive methods. And there are some problems with choosing priors, some philosophical issues that still haven't been resolved with Bayesian methods, but not something you would regularly meet in practice. Okay, so Bayesian statistics, I feel, are very important. Okay, let's start with a very, very, very simple example. So this is a Bayesian take on logistic regression. So we have our 1, 0 target variables, y. We have our data, which is x, a vector. And we're interested in learning the coefficients that tie that linear term transformed with the inverse logit function with the outcome, which is a binary variable. Okay, so very simple model, but already there's no way of analytically deriving the posterior distribution. So what we typically do in practice, and if you attended the previous session, we saw that we used a well-known Laplace approximation to this model. But if you're interested in more information about the posterior, you would typically use a Markovitchian Monte Carlo method, in this case Metropolis Hastings. Okay, so just to overview our work, we're working Bayesian methods, which kind of means that we are also often working computational methods. And this work that we're going to present now is part of our ongoing project on parallelizing these methods so that it can be used on a very general set of models on the GPU. So single workstation, fast Bayesian inference. Okay. And so this is the big picture, and the sort of more narrow view of this paper is that before we can get to those complex methods and very general classes of models, we have to start with simple models. So again, let's look at this Bayesian logistic regression. As I said before, there is no analytical way of deriving the posterior. But there has recently been a very interesting development in probability theory and Bayesian statistics that you can, using what we'll see as a new distribution, not very known distribution, we can use this data augmentation technique to derive a Gibbs sampling scheme for this model. So we can sample from the posterior by we can start with either one. So we can sample using these weights, some predefined weights. We can sample the beta from a multivariate normal distribution, and then we can, with the beta known, we can sample the weights from this distribution. And if we iterate this procedure, we're going to get eventually a distribution that converges in distribution to our target distribution. So Gibbs sampling is faster and more efficient than metropolis casting. So this was a very interesting achievement. And it's even more interesting because it doesn't apply only to Bayesian logistic regression. It also applies to multinomial regression and also to some very interesting count models. So it covers quite a big chunk of what the models we typically use in practice. Okay, so what we see here is that, so I can do Gibbs sampling if I can draw samples from the multivariate normal, if I can compute these, which are basically just matrix multiplication, transpose, and matrix inverse. So these are all operations that already have very good implementations on the GPU, very efficient implementations. But this, sampling from this new distribution, which is the Polya-Gamma distribution, is something that hasn't yet been done. So in order to have a fully GPU-optimized model, we need to kind of find a way of efficiently sampling from this on the GPU. And that's basically the story of this paper. Just a few things that are... I'm going to skip the actual algorithm, the initial algorithm, because it's too complex to cover in this presentation. I'm just going to start with a very useful property of the Polya-Gamma distribution, which is if you have two variables from a Polya-Gamma distribution which have the same second parameter, you can get a sample from the sum of these two distributions by sampling from a Polya-Gamma distribution which has the first parameter as the sum of the two parameters. So that's very useful because you can, for integer h, you can basically sample from Polya-Gamma h z by sampling from 1z h times and then just adding it up, and that will be your sample from your Polya-Gamma h z. So why is that useful? In all of the cases, basically in count inference, in discrete inference, these are integer. So if we can parallelize this, we then have a parallel procedure for sampling from any kind of scenario where we would meet this Polya-Gamma distribution. Okay, just a quick overview. This is not our work. This goes back even from Paulson back a couple of years. There was an algorithm for sampling from Polya-Gamma 1z. It's a rejection sampling based algorithm and has some approximations in it and an iterative approximation. You can see it in the paper summary, or you can go to the references. I'm not going to cover it. I'm just going to say so that this core algorithm of sampling one sample from Polya-Gamma 1z will be our unit of parallelization. So that's what we worked with. We didn't go deeper in parallelizing the sampling. Okay, so in practice we would meet, depends on our case, but we will probably, the typical scenario is we have to sample from multiple Polya-Gamma distributions with different A or H parameters and possibly different Z parameters. So a lot of these at the same time, we want to do that efficiently. So that's where I'll quit and let him take over, because this is the part of the project I have no idea.
Okay, so just a quick overview of what a GPU is and what you have to do to make an application suitable to run on a GPU. GPUs have been used now extensively for 10 years for general purpose computing. This is not a complete guide. This is just a quick overview. So a GPU typically consists of a large number of simple, we could say dumb, compared to the CPU, simple cores. They are very fast when dealing with straightforward math, mainly matrix algebra or any kind of math, but are slower when the tasks or the threads that we run on the GPU have divergent branches, have many branches, have uneven workloads, and so on. That's when GPUs start to the performance start to decrease. They also have very little limited local memory compared to a CPU core, which means that threads need to have small states. They don't. We must not keep many information about the thread all through the life of a thread. So, based on these properties, we know two things. We want to have a large number of threads, but not too many, because if we have too many threads, the workload becomes small, and the overhead of creating a thread beats that beats the benefits of creating one thread. And we want to have homogeneous threads, so even workloads, not too many branches, and so on. Okay, so the basic case of sampling from polygamma would be this. So we want to have R samples from polygamma HZ. We took a bit more complex approach of handling multiple such samplings. So R samples from one set of parameters, H and Z, R2 samples with different parameters, R3, and so on. We want all these samplings to be done at once. Okay, so the basic idea, the naive approach of parallelization would be, if we define a task, to be each sampling would be one task. The number of all tasks or threads, whatever you want to call it, would be the sum of R's. We get, with this approach, we get two problems. The first one is that the thread's workload is uneven. The thread with larger H and Z mainly have bigger workloads and would be stalled compared to the samplings with smaller H and Z parameters. And the other problem is that this number of tasks, this sum, can be small, and we want to have a bigger number of tasks available because we have many cores available to compute. So, based on the properties that Erik mentioned before, we split the samplings into smaller parts. Each rectangle is a sampling from polygamma 1Z, not HZ anymore. And instead of having uneven samplings, we basically restructure the problem to having many of the same samplings from 1Z polygamma distribution. The number of tasks we get in this way, if we define that each thread does a single sampling, would be the sum of R, the product of R and H, which can, of course, be bigger than the previous example if the H's are larger than 1. The question is this efficient? The answer is maybe. And we don't want to have an answer that is maybe. Why maybe? Because it depends on which GPU you use. If you use a low-grade old GPU on a laptop, this could maybe be efficient, but mostly no. So, okay, you can take 2 samplings with one thread, or you can take 4, and so on and so on. The answer would still be, is this efficient on every GPU, would be no. So the question is, what's the optimal batch size? There is no single optimal batch size because it depends on which GPU you use. We will get to that a bit later, how to get the optimal, how we got the optimal batch size for our solutions. Okay, so that's one problem we had to take care of, and the other one comes from the GPU's architecture. So I said before, a GPU is a set of simple cores. So these boxes are again now cores. Okay, these cores are split into groups. Different vendors term that groups differently, so I'll just say that these are groups of cores. And threads also get assigned in groups, and each group gets assigned to one GPU. Now the question is, how big should this group be? Again, we don't have a definite answer for any architecture. Why? If we have two smaller groups, the GPUs inside one group, the cores inside one group could be inefficiently used. If the group size is too big, we could have potentially another group of cores that would not get efficiently used. So again, what's the optimal local workgroup size? It depends on which GPU you use. Okay, we in our first approach that we took with this paper, we basically searched the whole search space that was narrowed down by the expert knowledge on the GPU architectures we used. And the batch size, as I said, and the batch size and the workgroup size, or the thread group size, depends on a lot of factors, number of cores, local memory, and so on and so forth. So with this approach, we took two GPU configurations. One is a laptop integrated low-end Intel graphics card, and the second one is a mid-range gaming that we would typically find in a desktop setting. So with the desktop setting, the speedups got to around 100 fairly quickly, and with the laptop setting, we got to about 30. We got substantial speedups of around 30, 40, even for small data set with, I don't think, 700 samples and 5 or 6 input features. Okay, so that's the main result. The future work includes, this first step of future work was already done. So small number of threads, so improved performance for small number of threads. The current code outperforms the CPU when the sum of product of R and H is around 1,000. So that's fairly optimal, or some. So the GPU is faster for practically all cases when we use this algorithm. We want to have offline and online optimization, so we don't have to search the whole search space every time we use a different GPU. Offline means that the batch size and local workgroup size are defined beforehand, and online optimization means that they are corrected during the execution. And we will also implement not only this polygamma distribution sampling, but whole algorithms for multinomial logistic regression, negative binomial account models, and so on. So that's it. Thank you.